Now, our very last little topic of this chapter is to go back to our third property of a conductor, so property number 3, which states that the electric field just outside a conductor must be perpendicular to the surface, and the magnitude of the electric field is sigma over epsilon naught, where sigma is the area charge density of the conductor, charge over area. So we're going to go ahead and prove number 3. Got number 4 left in here, more or less for completeness, but we won't really discuss that one until we get to our chapter about potential. So as we get started, let's assume we have a conducting surface. I've only shown a part of a surface here. You can imagine the full conductor if you wish, say a big bowling ball type object or something. We'd like to find the electric field, so we know we're going to use Gauss's law, so we know we need to pick a Gaussian surface. For my Gaussian surface, I'm going to pick a cylinder, which is partly inside and partly outside. You can't pick any shape of an object you wish. I'm going to do a cylinder just because the geometry is kind of easy to use. So a cylinder, part inside and part outside. So let's draw my cylinder. So there's my cylinder. It's partly inside, partly outside. The area of the face of the cylinder, I'll call that A. So let's deal with the direction first. What's the direction of the electric field vector relative to the surface? The answer to that question is it's perpendicular to the surface. Okay, well, why is it perpendicular to the surface? Let's take a contrary argument and let's ask what would happen if the electric field were parallel to the surface? So sometimes that can be a good approach to this surface. So if the component of electric field parallel to the surface, I'll call that E with a subscript of parallel, if that wasn't 0, well, what would happen would be that the force on each charge on the surface would be given by the charge times the electric field. That wouldn't be 0. And if that wasn't 0, then the acceleration of the charge on the surface, that would be the force divided by the mass, that wouldn't be 0. That would mean there would be motion of the charges. They would be accelerating. So charge at surface would move. That would violate our condition of static equilibrium. So then our conclusion is that the component of electric field parallel to the surface must be 0. So if we have a charge, then the only component of electric field we have would be perpendicular to the surface. So on the surface of our conductor, we can go ahead and draw our electric field everywhere. I'm going to make sure to put one going through my Gaussian surface. So there's our electric field vector parallel to the surface. Okay, next I would like to figure out what the electric field is. I think I've filled up this slide enough. I'll move on to the next one. To find the magnitude of our electric field now, we'll use Gauss's law, which states that the net electric flux is the integral of E dot dA, the integral of the electric field over our Gaussian surface, which is the cylinder that we drew. That's equal to Q enclosed divided by epsilon naught. We can do Q enclosed first if we wish. Q enclosed is how much charge is enclosed by this Gaussian surface. None of the charge is off the surface of the conductor. None of the charge is inside the conductor. All of the charge is on the surface itself. So the area is the same as the area of the face. So the total amount of charge is going to be the density times the area of the face, which we called A, equals density times area. That's the area of the face of the Gaussian surface, which is a cylinder. So I'll say area of the face of the Gaussian cylinder. Okay, that's the Q enclosed bit. What about the integral of E dot dA? So now our shape, our Gaussian surface is a cylinder. Our cylinder has three parts. It's got a top face, it's got a bottom face, and it's got the walls of the cylinder itself. So our total electric flux is going to have to be the integral over the three bits, top, bottom, and the walls. So the top and the bottom or the tube. So the flux of the top part, let's write that down. Flux of the top part is equal to the integral of E dot dA equals the integral of E times dA times cosine of 0. So the direction of our dA is a little bit of the area of that face. It sticks straight out, perpendicular to the surface. And our electric field is straight out. It's also perpendicular to the surface. So we've got cosine of 0. Integral of E times dA equals E outside of dA. E is constant. If we're a constant distance away, equals E times A. Now, we don't necessarily know what the area of this face is, but we have called it A, so we'll just leave it as A. Okay, what about the flux through the bottom of the tube? Well, there's no electric field inside a conductor. So equals E dot dA equals integral of 0 dot dA equals 0. So no electric field inside the conductor, therefore no flux through a surface inside the conductor. What about the walls of the tube? Well, we've got the integral of E dot dA equals the integral of E times dA times cosine. What's our angle on the side? Well, if we pick a little area element on the side, the area sticks straight out. It's perpendicular to the tube, which means it's parallel to the surface. Parallel to the surface is dA, perpendicular to the surface is E. The angle between those two things is 90 degrees. Equals 0. Okay, we're ready to use our Gauss's law now. So the net electric flux is equal to the integral of E dot dA over all three surfaces equals Q enclosed over epsilon naught. Our net flux is going to be EA plus 0, so equals E times A. That's equal to our Q enclosed, which was sigma times the area, divided by epsilon naught. So our electric field magnitude, we see that our areas cancel, is sigma over epsilon naught. Electric field is a vector, of course, so we'll add that it's perpendicular to the surface. And then if we wish, we could add in another note. We could say it's out if the charge is positive, and it's in or inward if negative. That concludes our chapter 22. So now we've covered Gauss's law really well in electric fields. Next, we're going to move on to something which may be a little bit familiar to you, which is all about energy and potential energy. It's just now we'll be talking about electric potential energy.